Okay, so what I'm going to do is continue this development of the periodic table. There's a lot more details to this that we haven't talked about yet. Now you'll notice I've got some letters, S, P, D, and F. Electrons are organized into those areas. Now, what we're going to talk about in this class are S, P, and Ds. When you get to 1A, you're going to talk about the Fs. The Fs are tricky. All right, so let's talk about the periodic table a little bit more here. Originally, I mentioned that we had groups, which are columns, and we had periods, which were rows. Okay, there's another name we're going to be using for the rows for this subunit, and it's called a shell. And there are 7 of them. So this would be a shell, this would be a shell, etc. The shells are subdivided into subshells. And those subshells are subdivided into orbitals. And the orbitals are how the electrons are organized around the nucleus. Because some of the earlier models, the electrons had no organization whatsoever. The first person to put organization to that was Niels Bohr back about 130 years ago. And he suggested a planetary model of the electrons traveling around. And the electrons were restricted to those orbitals, no other place. Excuse me. The inner orbitals held fewer electrons than the outer orbitals because they were smaller. They couldn't put as many in. And remember, electrons don't like other electrons. Charge on an electron, as you know, is negative. Negative and negative repel. So the smaller the orbital, you can't put too many in there because they want to repel each other. There are some things about Niels Bohr's model that didn't work, but it was a model that was used for a long time. And then along came the quantum mechanical model. And that model is where these S, D, P, and F regions come in. And this is the way they're organized. Okay, so if we look at now, you need to know these regions, by the way, for Saturday. So these are S's. These are P's. And these are lowercase, by the way, too. Those are the D's. And the F's are down here. Now, we're not going to do anything with the F's in this class, but you will in 1A. The D's are tricky enough. When you get to the F's, they're even trickier. Now, when we say these S electrons, they're shaped in a certain way around the nucleus. They're shaped spherically, and they're equally distributed around the nucleus. And you can have up to 7 layers of them if you have enough electrons. The p orbitals are shaped along the XYZ axes. And they're outside of the S's. So first the S's come, then the P's. Because there are three kind of sublobes of the P's, it can hold more electrons. It can hold 6 electrons. The S's can only hold 2 electrons. And then there's the D's. The D's are weird shaped. They fit in between the S's and P's. They're very odd. And the F's are even wilder. Because the D's take up more room than the P's, they can have up to 10 electrons in their orbitals. So we go 2, 6, 10. And those are maximum number of electrons. You can have just one in there, but you can't have any more than those numbers. Now, we're going to be just doing something today called electronic configuration. And what we're going to be doing is we're going to be cataloging every electron in the elements. So if the element has 6 electrons, we have to account for all 6 electrons and where they're located and what orbital they're in. So let me show you the way the cataloging goes. Okay, so let's look at helium. Okay, helium has 2 electrons. And notice helium is in the S block up there. And remember, how many electrons can fit in the S block? 2. And helium has 2. So it's going to fill up the lowest level S orbital, which is 1s. So the electronic configuration for helium is shell 1, subshell S, 2 electrons. So the shells can go up to 7. The subshell is either going to be S, P, D, or F. And the superscript there is going to be the number of electrons in the subshell. In the subshell. Okay. Along with that, you're going to have an orbital diagram with those electrons in there. So we have 2 electrons for helium. We represent it by these one-sided arrows. Now, the reason why they're going in opposite directions is because Electrons not only have a charge, they have a magnetic component to it as well. That's why electricity has both magnetism and moving charges. So electrons have the same thing, only at much smaller scale. Now, the big deal is if we have two magnets together, what's the easiest way to put two magnets together? North to north, south to south, or north to south? North to south. Everyone knows electrons attract or push apart. So for stability reasons, we want the electrons' magnetic components to be north to south also. Now, quantum mechanics describes all this stuff in immense mathematical gobbledygook. I mean, it is wild, the math in quantum mechanics, which is why chemistry majors and physics majors have to take lots and lots and lots of math, way past calculus. You're doing differential equations and matrix calculus and all kinds of stuff. Okay, so that's helium. You can also draw this, instead of a circle, you can draw as a box. Depends on what whose textbook you're looking at. Some do boxes, some do circles. So you guys can do whatever you want, boxes or circles. Okay, so let's look at this orbital stuff a little more detail here. So whenever we have an S subshell, we have one orbital. Because in each orbital, you can only have two electrons. So 2 into 2 is 1. P has 6 electrons. So how many orbitals can the P subshell have? 6 divided by 2. Right. So it's going to look like this. And then D is going to be 10. Now, per shell. So we keep breaking this down to finer and finer detail. We start at the shell, then we look at the subshell within the shell, then we look at the orbitals within the subshell. So 3 layers. All right, so let's do another one here. Got a whole bunch of these already done here. Let me see. Let me just start over here. Okay, so let's do carbon. Okay, so how many electrons does carbon have? What's the atomic number for carbon? 6. How many are core? 4 valence, 2 core. Remember, count up from left to right, 1, 2, 3, 4. All right. So we have to count for 6 electrons total. 2 core, 4 valence. And by the way, this is the guts of why certain atoms are more stable than other ones. What we're doing today. Okay, so we start off with the lowest shell first. Okay, shell is 1, and there's only 1 subshell in shell 1. And how many electrons can go in that? 2, exactly. So we've accounted so far for 2 of the electrons. And those, by the way, are the core electrons. Okay, We have 4 more to go. So now we're going to start at shell 2. Now in shell 2, there are both S's and P's. Okay, so if you look at the periodic table, here's shell 2. Notice in shell 2, we have an S subshell and a P subshell. Notice carbon is right over here. Oops, wrong screen. Here's carbon. So once you look at now shell 2, according to this, I'm going to start filling shell 2 now. First thing is the S's come before P's because they're more stable. So how many electrons can we put in that S orbital? 2, exactly. So that takes care of 2. And how many do we have left over? 2, exactly. So that's what's going to go in the next sublevel up, P's. Okay, so we're going to put 2 in the S and 2 in the P. And that's what carbon's electronic configuration looks like. 1s2, 2s2, 2p2. Let's look at the orbital diagram. I'm going to string these out. Now remember, the P's have 3 orbitals because it has the potential to have 6 in there. S's has 1, they have 2 maximum. Okay, so let's start putting electrons in those orbitals. Now notice I'm going to start left to right. Now when we get to the P's, there are 2 ways to do the P's. I'm going to show you the most unstable way first. So now we have all 6 electrons accounted for. 2 here, 2 here, and 2 here. But notice there's empty orbitals over here. Remember we talked about electrons, they don't like to be next to one another? So what is another way we could distribute those electrons to minimize repulsion? Your hand was doing the right thing. Yes, instead of putting them all in one orbital, we'll spread them out. That'll minimize the repulsion and it's much more stable. And the direction of the orbitals does not matter. I mean, the direction of the arrows doesn't matter. Okay, so that's the most stable configuration for carbon. There's a whole bunch of physicists that came up with this, and that technique is named called the Aufbau principle and all this stuff. You don't have to worry about that. The main thing is knowing the reason why the electrons are spread out. Because the P has the capacity to have 6 electrons, 2 per orbital. But we don't have enough electrons to fill that. So it's just there. It's just like a little cubby that doesn't have anything in it. Okay, is everyone okay with this? And like naming, you have to do lots of practice. All right, so let's do some more here. Another little accounting. The superscripts have to add up to the total number of electrons. The superscripts are how many electrons are in each subshell. So if you don't have enough superscripts to go around, you've left something out. All electrons have to be accounted for. All right, so let's do sodium. Okay, sodium has 11 total electrons. Period includes everything across. So no, no, and this is S. The helium is S. So that S applies only to that.
Okay. I just wanted to be sure.
Okay, sodium got 11 electrons. So we're going to do the same process. We're going to start at the level that's the most stable, the one level, the one shell, and start filling up orbitals and subshells and all that stuff till we get to 11 electrons. So we're going to go 1s2. We have 9 more to go. 2s2, 2p6. And we have 1 more to go. So that'll be 3s1. So that's what sodium looks like. Yeah, we just kind of keep going. Think about your uranium. Uranium is at the bottom of the periodic table in the middle. You will in 1A. We're going to go down to level 3 only. I'm not going to go any further than that because I want to make sure you guys really get this. Yep. Okay, let's look at the orbital diagram now. I'm going to spread this out. So just like before, now I'm going to fill it all in. Notice how I filled in the P's. I did 1, 1, 1 before I started pairing them up. So this is what makes up the core electrons. Notice that all the orbitals are full. That's why the core electrons are so stable, is the orbitals are all full. And if you look at the inert gases, which we are in a second here, everything is full. Now with this sodium, notice the valence, that s orbital there, is half empty. It's not full. So that's one reason sodium is less stable than neon. It's because we have a non-fully filled orbital. Yeah. And that's why sodium likes to lose that electron and become a cation. So it will mimic neon. Okay, so when you form ions, ions are going to be losing electrons, gaining electrons. When you lose electrons, you have to lose electrons so that you gain stability. Otherwise, there's no point in becoming an ion. Gain electrons for stability. Otherwise, what's the point again? So they lose and gain electrons strategically to maximize the stability of the ion based on filling those orbitals. Yeah.
Yes. Getting the 2p. Move on 1, 2, 3.
Shell 2 also has these p electrons orbitals available.
Yeah.
So we have to fill them up.
What? I thought we were just dealing with sodium.
We are. Sodium's got 11 electrons. Right here. Those are P's. These are all P's except for that helium. So every atom has the capacity of having a whole bunch of orbitals. Most of the time, they're empty, though, because not enough electrons. So we start plugging in electrons. We have to put in the ones that are the most stable place for them to go, which are the lower shell numbers. Okay, so we have a 1s place to put them. We have a 2s place to put them, a 2p place to put them, a 3s, a 3, a p, a 4s, a 3d, a 4p. All those are potentially places we can put them. And the electrons go in the most stable place first. That's why we fill the low ones first. So the more you move to the left on this line down here with the orbitals, the more stable those electrons are. So if you wanted to pull an electron out of that atom, the one hardest to pull out is going to be the one closest to the nucleus, or the 1s electrons. Those are super hard to pull out because they're so stable. They're nice and close to the nucleus. Nucleus is positive, electrons are negative, nice attraction there. It's going to take a lot of energy to pull it out. The outermost electrons come off the easiest because they're the furthest from the nucleus. Stability rules the game. And something is super stable, it's going to take a lot of energy to take it apart. If it's real unstable, it doesn't take much energy at all. It just comes right apart. And that's why ions form. Stability reasons. Electrons come, electrons go. Okay, so as you go in increasing shell numbers, you have to account for all the subshells previous to that. You have to make sure those are all full first. That's why we had to fill in these P's before we got to the 3s. Okay. And core electrons will always, no exceptions, have all the orbitals full. That's why the inert gases are so stable. You need to know that. Okay, so is everyone okay with sodium? All right, what we're going to do now is we're going to do silicon. So silicon has about 14 electrons. So we have to count for all 14 now. By the way, uranium has 92. This is what we do for uranium. Exactly what we're doing here. Only you have to count for 92 electrons. Every single one has to have a designation. Okay, so we're going to do the same thing. Start off with the most stable orbital, and it'll hold 2 electrons. The next one is okay, so how many have we accounted for so far? 10, right. So we still have 4 more to go. That's 12. 14. So look at the valence on carbon. 2s2, 2p2. Look at the valence on silicon. 3s2, 3p2. They're exactly the same, except they differ by a shell number. But the s's and p's are the same. If the valence configuration electrons are the same, the chemistry is going to be the same. That's why everything in that group has the same chemistry, is because their electronic configuration of the valence electrons is the same. So valence electrons is where the chemistry happens. If the valence electron configurations are the same, chemistry is the same. Okay, so let's look at the orbitals here now. So let's go ahead and fill those all in. So that's what the orbital diagram looks like for silicon. So again, when we fill these in, we have to account for the most stable orbitals first, which are those low shell numbers. Now, uranium is going to be at shell 7. That means you have to account for the 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s. All those are going to be filled in as we come up with 92 electrons. That okay, so those two illustrate again why the chemistry of groups is the same. The core electrons are not different. Silicon just has more core electrons. But the valence electrons are exactly the same, 4 and 4. And their orbital diagrams are exactly the same. Hence, the chemistry is the same. Okay, now, yeah, because it's the outermost orbital. The electrons on the outside are the valence. Yes. Yeah. And these would be core. Mhm. But it may not be full. Think of a mailbox at an apartment house. Yes. Yeah. 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 And we're going to add D's in here in a minute here. Yeah. But just think of a big apartment mailbox system. You know, everyone gets some mail, some people get no mail, but the boxes are still there. So the orbitals, yeah, so the orbitals are there, they just aren't filled. Yeah. Okay, so the order. One way to remember this order is to look at the periodic table. So if we find ourselves at silicon, look up above it. What's up above it? Well, we have S's and P's before it. And as you go from left to right, first you hit the S's, and as you travel across the periodic table, you hit the P's. Yeah. So there's an order there. Okay. So our question was regarding order. Okay. For shell 1, that's only S's. Shell 2, you can do S's and P's. Shell 3, you can do S's and P's. Shell 4, you can do S's, D's, and P's. I'm going to do one of those in a minute here. I want to make sure these guys, you understand these guys first, though. Okay, so let's do iron. Oh, it's already done. How about that? Okay, so let's do iron now. Now, there's a weirdness when you get to the D's. And even more weirder are the F's, but the D's act a little differently in terms of stability. There's a little anomaly between the D's and the S's. And it appears at the 3 level. So let me show you what I'm talking about. Okay, see, iron has 26 electrons. So we're going to go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And how many electrons do we have here? So we have 10, 20. So we have 6 more electrons to deal with. Okay, so notice where iron is located. Iron is right in the middle of the periodic table in the D category. Now, as a way to remember how the D go, I want you to think of the word dumb. Okay, D for dumb. So when we get to the D's, we're going to dumb it down by 1. In fact, when we get to the S, those are failures. We're going to dumb it down by 2. Okay, so as far as our class is concerned, there's have to worry about the D's. So the D's are going to be dumbed down by 1. And that's the shell number is going to be dumbed down. So right now, we're at shell 4. So if I'm going to dumb down 4, what's it going to become? 4 minus 1. And how far into the D's are we? It's what? 2, 4, 6. So that's iron. Then we get to the P's when we be back up to the 4 level again. So just that section of D's in the middle, down by 1. When you get to 1A, you're going to find the F's are down by 2. And again, it has to do with stability anomalies. Six electrons in the D shell. So if you start in D in the middle, though, over 6 places.
What's the 3?
It's the shell number. Remember, the first number is shell, the next is a subshell, and the superscript is how many are in that subshell. So for the D's,
The 3rd shell.
yeah. That's why I called it an anomaly. It's weird. Yeah. Maximum. You'd have to have 10 electrons available to put in that. But we only have 6 to put in. So, all right, so let's look at the orbital diagram. How many orbitals for the D? 5, right. Okay, so let's just start filling them in. Now, same applies for the D's as the P's. We're going to go across 1 in each one. So that's the orbital diagram. Yeah, exactly. Okay, so that's iron. Now notice iron, the way it is, isn't particularly stable. It's got a whole bunch of empty or half-filled orbitals. That's why you don't find iron, shiny iron, sitting around the yard. Because it's not particularly stable in the metallic form. So you've got to protect it if you want to keep it shiny, put some varnish on it or something like that, or paint. Otherwise, it'll combine with oxygen and form ferric oxide or rust. Rust is much more stable than metallic iron. Rust has got its orbitals all full, unlike metallic iron. Okay. So to analyze whether an element is stable in its native form, neutral form, these are the 4 rules you got to go by. So number 1 is the strongest, full shell. And there are 7 of those. Those are called the inert gases. Full subshell. So if some of the subshells are full and some aren't, but you've got one that's a full one, that lends it to more stableness than if you have something else. Half full is also stable. Not as stable, though, as a full one, but still stable. And then lastly, if you don't have anything, wishy-washy, the subshells are all half full and or partially full, whatever, nothing. So this is what, 1, you use to analyze whether something is going to be stable. Number 2, it also affects, when an ion forms, how it's going to form. Is an electron going to add to stability? In other words, moving it up? Is taking away an electron going to add to stability? So let's look at iron now. Okay, iron is not full shell because the 4 P's are still empty. And we also have some D's that are only half full. So it's definitely not number 1. Is it number 2? And we're not considering the core electrons, only the valence. Remember, that's what determines chemistry. So do we have any full subshells? Yeah, we do. We have the S at 4s. That's full. Its capacity is 2. We have 2 in there. Do we have any half full subshells? No, because the D's are neither full nor half. So what can we do to make iron more stable by forming an ion? What could we do? Huh? Yeah, which one? That's perfect. Which one? Which one? The D's? Which one? You're right so far. Which one, though, of the D's? There's 6 there. Yeah, exactly. Perfect. All right. So if we took away the down arrow in the D's, this guy here, we now go from a partially full to a half full subshell. We just raised it 1 on that. So that's why iron forms a +1 ion. because by pulling out that one electron from the Ds, you create a half full subshell. Hmm? Yeah. Another negative ion, like oxide, for example. Okay. We can also remove all the Ds, all 6 of them. So by pulling off that one, we're going to end up with iron +1. You can also pull off all the Ds, end up with an iron +6. Which do you think is easier to do? Pull off 1 or pull off 6? Pull off 1. So the iron 1 is much more stable than iron 6. That's not to say that there aren't any iron 6s out there. I'm sure there's 2 in the world. My point, though, is 1 is much harder to do. It's easier to pull off 1 than to pull off 6. And that's why ions form. If we go back to, are there any questions about that? If we go back to sodium, okay? Now that's sodium metal. Very, very, very rare in nature. Why do you think it's so rare? You always have answers.
I know it.
Yeah, that last 3s electron is sitting there. What could sodium do to become much more stable? Lose it. Lose that electron. Now it becomes, and notice what happens. If we analyze, once that electron's gone, we have a full shell. That's the ultimate stability. So that's the big driving force for sodium to lose 1 electron. Because it's incredibly stable now compared to what it was as metallic sodium. So if you buy sodium metal, you have to buy it covered in oil to protect it from oxygen. If you take sodium metal, drop it in water, it immediately reacts. Immediately. Hanford up in Washington State had tons of sodium metal they created through some fission and fusion processes they had to get rid of. So they dumped it all in this lake. They boiled the lake. Boiled. because the sodium metals are reacting with the water. In fact, it forms sodium hydroxide, lye. They were pickled. You can lose many electrons, but the more you lose or gain, harder it is. If you look at now from your naming, what's the charge on oxygen, oxide? -2. Let's see why it's -2. Okay. Oxygen has 8 total electrons. So if we do the orbital diagram for that, okay, so there's two ways to go with oxygen. One way is to lose this down 2p. So you form an O plus 1. But we know there are not a lot of O plus 1s around. There are mostly 99.99999%. It's -2. So if oxygen can gain 2 electrons, 2 in the p orbit there, it becomes a full shell. And that's why oxygen forms a -2 anion. And also sulfur does, because sulfur has the same valence as oxygen. So it's going to do the same thing. Forms a -2, yeah. Yeah. Oxygen, the world is full of oxides. When you mine an ore, it's always the oxides. When you go out and mine uranium, guess what it is? Uranium oxide. So you got to do some reactions to remove the oxide if you want the pure metal. And oxide, it's forms readily an anion, readily. And then all these metals, all the metals form cations. So they're looking for an anion. And here's oxide. So that's why you see all the metals with oxides. That makes sense? You look at the bottom row on the periodic table. Those are valence electrons. So count over 6 for oxygen, and then you account for 6 going this way from right to left. Now those are the valence. Or basically, you look at the shell. It's the highest shell number. Yep, exactly. As long as they're in the same row, those are all valence. What gets weird though is when you get into the D's, those are valence, but they're different kinds of valence. Okay, that's what I wanted to cover today. We're done with unit 3. So you're going to have some of these on the tests. You're going to have some naming on the tests. I'll put out a study guide as well. And there's some worksheets on that zipped file. Again, doing this, I believe. I need to look. Oh, yeah. You see a pattern? Yeah, and they're all the same. Can't remember you were saying the pattern. That's why I said, did you get the pattern? Okay. Could someone send me an email to remind me to put out a study guide? Next Saturday, yes. There'll be in-class tests.